Previously, we defined a multiplication between two vectors called the dot product. The dot product was the magnitude of u times the magnitude of v times cosine of theta, which is the angle between u and v. The dot product produced a scalar, just a number, when you found the dot product of two vectors. Now, the reason we used a dot product was to find the projection of a vector u onto a vector v. So that was the application that made dot products useful. Now we want to look at another multiplication. This multiplication is called a cross product. And we'll represent it as u cross v. Now u cross v comes from an application in physics where, let's say that we have a pivot point and we have a force which is represented by the handle of this wrench. So we'll call this R. Then we're going to apply a force to the end of that handle, F. And there will be an angle between R and F, which is theta. Now, when you apply the force F to that handle R, you're generating a twisting action in a plane, in a direction that's perpendicular to the plane containing R and F. Now, that twisting action depends on three things. It depends on the magnitude of R, the magnitude of F, and the angle that F makes with R. Okay, now that twisting action is called torque. It ends up that if we found the cross product, U and V, in this case R and F, so R cross F, the magnitude of that is the magnitude of the R, so the length of that handle, times the amount of the force F, times sine of theta, where theta is the angle that's made between R and F. Okay, so that's what we're going to use cross products to figure out this amount of torque. So given two non-zero vectors, u and v, the cross product, u cross v, is a vector. So you'll actually generate a vector that's going in a direction that's perpendicular or orthogonal to the plane containing u and v. So the important thing about a cross product is that it gives you a vector, not just a scalar like the dot product. The magnitude of that cross product is given by the magnitude of u times the magnitude of v times sine of theta. Now theta is an angle, again, between 0 and pi. It's the angle between the vectors u and v. To determine the direction of u cross v, we use the right-hand rule. If you took your hands and pointed your fingers down u, and then curled them up so that the fingers were then pointing to v, the direction of u cross v will be in the direction that your thumb is pointing. It will be orthogonal to both u and v. So cross product is orthogonal to both u and v. Now, if u cross v is 0, then the direction isn't defined. A zero vector is not going to be defined. It doesn't have a direction. So notice if you have the vector u here, the vector v, let your fingers point down u, curl them so that they're then pointing down v, and where your thumb points is the direction that u cross v goes in. And then this gives us the magnitude of u cross v. So we can find the direction orthogonal to u and v and going in the direction. Remember, there's two ways it could go. It can go upward or it could go downward. And the right-hand rule says that u cross v will be going upward. Now let's look at some geometry. The vectors u and v will be parallel if and only if the cross product is 0. Now if you look at this definition, if the two vectors are parallel, that means they're either both pointing in the same direction, which means that the angle between them is 0, which remember that sine of theta, sine of 0 would be 0. So that means that u cross v will just be 0. Or if theta is equal to pi, then the magnitude of u cross v is also 0. So if the two vectors were going in opposite directions, meaning the angle between them was pi, then they also have a cross product of 0. Now, what that means, remember that wrench. We had the force R, and we had the force F that was applied at an angle theta from R. Think about that twisting action generated from applying that pressure F to R. If theta is 0, that means you're pushing on the end of the wrench. You won't be causing any twisting action in this vector. So when theta is equal to 0, there won't be any torque. Also, when theta is equal to pi, there will be no torque. Now, the biggest torque occurs when theta is actually equal to pi over 2. So if we applied the vector F at a 90-degree angle from R, that will cause sine of theta to be the largest it can be, which is 1. And we will have the greatest torque, the greatest twisting action in that vector that's perpendicular to that plane containing R and F, which will be just the magnitude of u times the magnitude of v, or the magnitude of R times the magnitude of F. So now let's look at another geometric property of the cross product. If u and v are two sides of a parallelogram, so we have the vector u, we have the vector v, and then we're going to draw lines parallel to u and parallel to v, creating a parallelogram. Now, if I were to find the area of that parallelogram, I know that the area is the base times the height. The base is just the magnitude of u. The height can be found by dropping an altitude straight down to u from the tip of v. Using the trig function, we know that sine of theta will be the height over the magnitude of v. So that means our height is actually the magnitude of v times sine of theta. So our height here is the magnitude of v times sine of theta, but that area is just the magnitude of u cross v. So one property that cross product has is that if you had two vectors u and v that were sides of a parallelogram, then you can get the area of the parallelogram just by finding the magnitude of that cross product. Now let's find the magnitude and direction of u cross v. In this, we're given that u is 1, 1, 0. So it's going to be a vector down in the xy plane, since the z component, the y component, the z component, which is the k component, is actually 0. And the vector 1, 1, 2, which is directly above that point 1, 1, 0, but at a height of the square root of 2. So this side of that triangle, that right triangle, would be the square root of 2. Now, to find u cross v, we need to find two things. We need a direction and we need a magnitude. To find the direction of u cross v, start your fingers pointing down u, curl them so that they will now point toward v, and so the direction that your thumb would be pointing would be in this direction. So u cross v will be orthogonal to that plane that contains u and v, and it would go in this direction here. Now the magnitude, we know the magnitude of u cross v is the magnitude of u times the magnitude of v times sine of the angle between them. So let's see if we can find the angle between u and v. Well, if you notice that this right triangle that we created has a height of the square root of 2, and this length from 0, 0, 0 to 1, 1, 0, that length would also be the square root of 2, just using the distance formula. So what we have is we have a right triangle with two legs, both the same, which gives us a 45-degree or pi over 4 angle. So calculating the magnitude of u cross v, we need the magnitude of u. Well, the magnitude of u will be the square root of 1 squared plus 1 squared plus 0 squared. The magnitude of v and then the angle between them is pi over 4. Sine of pi over 4 is the square root of 2 over 2. And we get just 2. Now these are some properties of the cross product. First, if you find u cross v, it ends up being just the negative of v cross u. So you don't have a commutative property for cross products. You can't just reverse them. It actually reverses the direction that the cross product goes in. Also, if you have a scalar times a vector u crossed with a scalar times the vector v, that's equivalent to taking the product of those scalars times that cross product of u and v. So that's called an associative property. We have a distributive property on the left using a cross product over a sum. So u cross the sum v plus w would be the same as u cross v plus u cross w. Likewise, we have a right multiplication for the cross product for the distributive property, whereas if you have a sum u plus v cross w, that's equivalent to u cross w plus v cross w. So we'll use these properties to find equivalencies in using I, J, and K in the next section.